Again. This is again a completely optional video, but I do want to talk about velocity-dependent forces. The big example of this is air resistance. So what we're going to do is let's say that there's an object and it's going to fall. So it's going to have a weight force, which is the mass times g. But it could also have a force upwards. All right. So in the free fall lab, I asked y'all to drop a sheet of paper versus a crumpled up piece of paper. And so this could have a force. And so for the moment, we'll call it R, which is going to be minus. All right, so there's going to be a velocity downwards. And we'll say the resistive force is minus some constant times that. So when we first drop it, so I'm going to do is a couple of sketches. We first drop it, there will only be the mass times g, and that never changes. The weight's fixed. But later on, after it's fallen a little distance, so this is v equals 0, v slightly greater than 0, then there'll be a upwards force, which can't be very big, but it'll have a non-zero amount. And then eventually, when v is approximately some maximum velocity, what will happen is you have equal forces. All right. So we'll have mg is dv, and so what we get is v, what we call the terminal velocity, will be mg over b. Now, we don't know what b is. It's just some constant. It has to do with the aerodynamic shape of whatever the object is. When you dropped your sheet of paper, wadding it up into a sphere was pretty good, and it lowered b as much as we could, effectively. You could have formed a dart and dropped the dart and gotten that better, but a flat sheet of paper had a very high b here. But what this is doing is it's sketching out the idea of your velocity over time. Well, the acceleration is highest in the early part, and it's 0 later on, and those have to connect up, so you expect something that looks like that. How do you get to that? Well, we look at the free body diagram, and we'll say that mg minus bv, so we'll take down as positive, is going to be our mass times acceleration. This is a not good equation. What this is mass times g is a constant, minus b dx dt is mass times d squared x over dt squared. Or alternatively, I'll write it a slightly different way. mg minus bv is m dv dt. So we can find an expression for the velocity probably a little bit easier, but this is a differential equation. So this is where I teach you how physicists solve differential equations. And the uniform sort of, in my experience, the way we do this is, 1, we already know the answer. 2, we look it up. 3, we ask a mathematician. 4, we give it to a mathematician to work on. And they find the answer for us. There are physicists who do solve new differential equations. They're generally considered mathematicians as well. Like, I'm At some point, when you're doing this work, you're doing mathematics. So, need to solve this. We can do a little bit of maneuvering around this and trying to figure out what's going on. But in general, whenever you have a function that looks like dx over dt is some constant times x, this generally looks like your constant is an exponential, like that. So that's what's going on here, is that we have um, an exponential function going on. And so we can express our velocity as a function of time as some initial velocity e to the minus, and then there's some expression up here in terms of, uh, actually it's not e to the minus, it's probably like 1 minus e to the constant, some constant here times t, right? And filling in that constant is going to come from these particular constants here, right? So I'm trying to remember this. I don't remember it off the top of my head. This isn't the point. The point is that you can have forces that vary. Those forces can vary with a weird dependence, such as the velocity, because this could also be a times v squared. We're not actually sure what it is. It depends on what's going on in what the shape is, what the speed is. We're not sure that it's actually either one of these. It could be in between. It depends on the type of motion. But this is what I want you to get out of it, is that this is why things have a terminal velocity. It's because they have air resistance, and the velocity can't just increase arbitrarily. It ends up getting to a point where the air resistance equals the weight force, and so the acceleration is zero. And until it isn't, it's an exponential. And I want to have you have this. So if you want to know more about this, please feel free to read it in the textbook. It is in there. But it's out of the scope of the class at the moment. Um, we're working on work and energy, and I'm showing you this because I think it's cool. It may come up somewhere else. So I may use this video somewhere else, but this is all I want to do right now.